In section 11.3, we also want to go over another type of chi-square test, which is the test of independence. The test of independence is usually used when we want to compare two variables. Okay, so in this case, we usually have a contingency table which shows all of the observed frequency for those two variables. And when we talk about two variables, you remember that any of those variables can have different categories as well. Okay, so contingency table is not only a 2 by 2 table because any of the variables can be classified into different categories. But all the numbers that are in the contingency table are the observed frequency. An intersection of each row and each column in the contingency table is called a cell. For example, if you look at this table shows the result of a random sample of 1984 undergraduate students classified by two variables. The variables are the student's living arrangement and the family college experience. We only have two variables, and by chi-square test of independence, we want to compare these two variables. But as you see in the table, each of the variables also classified into different categories. For example, the student's living arrangement is classified into 5 variables, 5 categories. If the student living with their parents, but they don't pay rent, or if they live with parents, but they still pay rent, or the students live on campus, or live off campus with others, or live off campus alone. And the family college experience is also classified into 2 categories. If the student is the first in the family going to the college, or if it's a second generation. So we have a 2 by 5 table. So we have 2 rows and 5 columns. And we always show the row by letter R and columns by letter C. And all the numbers in this table are the observed frequency. But you know that every time you want to use chi-square test, because the chi-square test that we use in this section, it's exactly the same as the chi-square test in the previous section for goodness of fit test. So if we want to use that chi-square test, we need both observed and expected frequencies. The numbers in the contingency table, it's observed frequency. Now the question is how we can find the expected frequency. To find the expected frequency, for each of these cells, we need to know this number is in which row and which column. Because, for example, 190 is in the first row and the first column, but 39 is in the first row and the second column. And to find the expected frequency for 39, you need to add all of the numbers in the first row and add all the numbers in the second column and then multiply together and then divide it by the sample size. So we use this formula for each of the cell, for each number in cells. So if you have a 2 by 5 table, that means we have 10 numbers in the table. So we have to use this formula 10 times. It depends where the number is, in which row and which column. So it's better to make this process faster. First, find the sum of all numbers in the rows and the numbers in the columns. So that's why we add one extra column for the total and one extra rows for totals. These numbers are the sum. This is the sum of the first row, sum of the second row, sum of the first column, the sum of the second column, third column, fourth column, and the fifth column. Then to find the expected frequency for 190, since 190 is in the first row and the first column, we need the sum of the numbers in the first row and the sum of the numbers in the first column, which means 386 times 841. And then divide this by the total sample size, which is 1984. And the result, after simplifying this fraction, gives me the expected frequency for 190. We do the same for 39. 39 is in the first row, which the sum is 386. It's in the second column, which the sum is 148, and then divided by the sample size. For this number, 428, the 428 is in the second row, and the sum in the second row is 1598. And it's in the third column, which the sum is 525, and then divided by the sample size, which is 1984. So we need to use that formula for all of these numbers. And you can see all of those calculations here. After finding the expected frequency, now we can start a hypothesis test. But you know, for hypothesis test, for a chi-square test, you always check the requirement. And the requirement is exactly the same as the requirement for the goodness of fit test. It means that the observed frequencies must be obtained from a random sample, and the expected frequency must be greater than or equal to 5. After checking the requirement, you need to write the null and alternative hypothesis. This is a test of independence. That means you want to see if the two variables are independent on each other or dependent of each other. So that's why when you are writing the null and alternative hypothesis, you use the word independent for the null, and you use the word dependent for the alternative. Okay? Because that's a test of independence. We want to see if the variable, the two variables, are dependent or independent. And then after writing the null and alternative hypotheses, like the goodness of fit test, we need to know the degrees of freedom because we want to use the chi-square table to find the critical values. So to find the degrees of freedom, we need to follow these formulas. R means the number of rows, C means the number of columns. If I go back to the previous table, you see that this table has 2 rows and 5 columns. That means if I want to find the degrees of freedom, I have 2 rows, which is 2 minus 1, 5 column, which is 5 minus 1, 2 minus 1 is 1, 5 minus 1 is 4, and 1 times 4 is, so the degrees of freedom for that table is 4. And then we look at the chi-square table by knowing the degrees of freedom and alpha, find the critical value, and after finding the critical value, you know that the rejection region is always greater than that number because it's a chi-square test, and the chi-square is a skewed right distribution. Then we need to use the same formula as the goodness of fit test and find the test statistic and check if the test statistic falls in the rejection region or not. If it falls, we reject the null. If it doesn't, we fail to reject the null. And all these steps are in this table, as you see. Now let's look at the previous example that we had it before, the contingency table for students living arrangement and the family college experience. So in previous slide, I show you that how you can find the expected frequency, and I put all the expected frequency in the parentheses here. So this number is the observed, and these numbers in parentheses are the expected frequency. So this one is observed, this one is expected. So we have all of the observed and expected frequency. So to start a hypothesis test, I will check the requirement. Are all observed frequency coming from a random sample? Yes. Are all expected frequencies greater than or equal to 5? You see, you look at the numbers inside the parentheses and you see, yes, they're all greater than 5. So yes, the problem satisfies all the requirement for the chi-square test. Now I can start writing the null and alternative hypothesis. And as I said, we use the word independent for the null and dependent for alternative. And since the two variables in these examples are the student's living arrangement and the family college experience, for the null hypothesis, we say the student's living arrangement is independent of family college experience. And for the alternative, we say the student's living arrangement is dependent on family college experience. And since the question is asking you, can you conclude that the variables are related? Related means dependent. Is asking you, the claim says that are they dependent? So that's why the claim goes for the alternative, because dependent is on the alternative. Okay, let's see if we can support the claim or reject the claim. So we need to find the degrees of freedom because we need to look at the chi-square table. So this table is a 2 by 5 table. So as I show you, 2 minus 1, 5 minus 1, it's 4. The degrees of freedom is 4. And you know the alpha is 1% because the problem is given to us. Now by having these two, we look at the chi-square table and find the critical value. And you know that the rejection region is always all the numbers that are greater than that critical value. Okay, now we need to use the chi-square test. So you know that the chi-square test is observed minus expected, and then S square, and then divide by the expected for all cells, and then add them together. So you can follow these steps in the table as well. So put all of the observed and expected frequencies in the table, and then in a separate column, subtract those numbers. In another column, S square the result, and then divide by the expected one, and at the end, just add them together. And you get the number for the test statistic. Now, to make our decision, we need to know if this number falls in the rejection region or not. So the rejection region means any number that's greater than 13.27. And this number is also greater than 13.27. It means I need to reject the null. And if you reject the null, since when you reject this one, that means you can conclude that the student's living arrangement is dependent on the family college experience. So we say there is enough evidence at what percent level of significance to conclude that the student's living arrangement depends on family college experience. Let's look at another example now. So feel free to pause the video, follow all of the hypothesis tests, and then check your result. This question says, a health club manager wants to determine whether the number of days per week that adults exercise is related to demographic cohort. So we have two variables, the number of days the adult exercise and demographic cohort. Okay, it means a generation. So we have two variables. We want to compare these two variables. We have a random sample of 275 adults, which is randomly selected, and the results are classified in this table. If alpha is 1%, is there enough evidence to conclude that the number of days an adult exercise are related? Again, related means dependent. And you put the dependent for the alternative. That means the claim must be on the alternative. I know so well by just reading this sentence. When you look at the table, you see that the number of days that the adult exercise per week, it classified into 5 categories. If they exercise 0 or 1 day per week, or 2 to 3 days, 4 to 5 days, 6 to 7 days. Oh, it's to four, sorry, that this is a total. So make sure to do not get confused with the total column like this. Okay, so we have 4 categories for the first variable and 2 categories for the second variable, which is the generation, if they are Gen Z, which is ages 18 to 24, or the ages is 25 to 40. And you know all the numbers in this table are the observed frequency. So we have 2 rows and 4 columns. You know that the first step is finding the expected frequency. The expected frequency for each of the numbers in cells is coming by multiplying the sum of the rows and the sum of the numbers in that column and then divided by the sample size. If I want to find the expected frequency for 40, I need to add all them because 40 is in the first row and the first column. First row and first column. So I need the sum of the first row. I need the sum of the first column, multiply together, divide by the sample size, which is 275. We do this for all of the numbers in the table. We have 4 times 2, which is 8 number in the table. We have to do this 8 times. After finding the expected frequency for each cell, now it's time to write the null and alternative hypothesis. As I said, for the null hypothesis, we put independent. For the alternative, we say dependent. So we say the number of days of exercise per week is independent of generation, and the number of days of exercise per week depends on generation. And we know that the claim is on the alternative. Okay. Now, I just skipped some steps so you can do it on your own, but we have 2 rows and a 4 column. If you want to look at the chi-square table, you need to have the degrees of freedom. And the degrees of freedom is r minus 1 times c minus 1. What is 2 minus 1 times 4 minus 1? 2 minus 1 is 1, 4 minus 1 is 3, and 1 times 3 is 3. So the degrees of freedom in this case is 3. Alpha is 5%. You look at the chi-square table and you find the critical value. After finding the critical value, you know the rejection region is always any number that's greater than that. Now it's time to calculate the test statistic. If you want to work on the problem manually, you need to use the formula. You need to subtract each of the expected frequency from the observed frequency and then square them, divide by the expected frequency, and at the end, add all those numbers. And I will show you, and for the next example, how you can use the online calculators as well. But if you use the technology and using the formula, in both cases, you will get 3.493 for the test statistic. We said in the rejection region that any number greater than 7 must be rejected, and this number is not greater than 7, which it means we fail to reject the null. If we fail to reject the null, that means we need to reject the alternative. An alternative was my claim, so I cannot support the claim. So we say there is not enough evidence to conclude that the number of days an adult exercise per week is related to generation, because that was what the question was asking. Are they related? Since we are rejecting that claim, we say we don't have enough evidence that they are related because we can't support it. And the last example here. In a volunteer group, adults 21 and older volunteer from 1 to 9 hours each week to spend time with a disabled senior citizen. The program recruits among community college students, 4-year college students, and non-students. In the table, there is a random sample of adult volunteers and the number of hours they volunteer per week. So we have 2 variables. the type of students, if they are community college students or four-year college students or non-students, which is 3 rows. That means the type of volunteer classified into 3 different categories. And the number of hours they volunteer per week is also classified into 3 categories. So all these numbers are the observed frequency. Now it's time to find the expected frequency first. To find the expected frequency, I need to know the row, the sum of each row and the sum of each column. I found it here. I put it in those shaded row and columns to make it separate from the numbers in the table. Now, to find the expected frequency for 111, the first one, I need the sum of the first row and the sum of the first column, and then multiply together, divide by sample size. For 96, I need the sum of the first row, multiply by the sum of the second column, divide by the sample size. And if you remember for the formula, we use the ER and CR, which means the number of rows and the number of columns. So for 111, we have E1 and 1. That means the first row and the first column. For 96, we have E1 and 2 because it's in the first row and the second column. 48 is in the first row and the third column. That means we need the sum of the first row and the sum of the third column divided by the sample size. Then after finding all of those, simplifying all the fractions, we get the expected frequencies. And I put all the numbers, the observed and the expected frequency all here in this table. Okay, now it's time to check the requirement. So go back to the problem. To check the requirement, you need to check if all the observed frequency coming from a random sample. Yes. We need to check all of the expected frequencies are 5 or more. And as if you look at these numbers, you see, yes, they are all 5 or more. So we check the requirement. Okay, next step, write the null and alternative. For the test of independence, or when you read the question, how you know that you need to use the test of independence? Because the claim says that is the number of hours volunteer independent of the type of volunteer? That means that's a test of independence. And you know that for the test of independence, we always put the word independent for the null and dependent for the alternative. And this time is asking if they are independent. That means the claim is on the null hypothesis. So when I'm writing the null and alternative hypothesis, I mentioned that the number of hours volunteer is independent of the type of volunteer, which is my claim, or the number of hours volunteer is dependent on the type of volunteer. Okay, after writing the null and alternative hypothesis, now I need to find the degrees of freedom. Degrees of freedom, it depends how many rows and how many columns do we have. We have 3 rows and 3 columns. So that means the degrees of freedom is 3 minus 1 times 3 minus 1. 3 minus 1 is 2, 3 minus 1 is 2, and 2 times 2 is 4. So the degrees of freedom is 4. Alpha it's given, it's 0.10. Okay, we look at the chi-square table. If degrees of freedom is 4 and alpha is 10%, what number do we get? We get 7.779. That's my critical value. And I know the rejection region is any number that's greater than this number. Okay, now it's time to calculate the test statistic. Test statistic means subtract all of the expected from the observed square divided by the expected. Okay, If I do that and add all those numbers together, I get 12.99. Okay? Now, we said any number more than 7.7 must be rejected, and this number is more than 7.7. It means it's in the rejection region. If it's in the rejection region, we need to reject the null. And the null was the claim. So that means we need to reject the claim. And if you reject the claim, it means that you say then you don't have enough evidence that they are dependent on each other. So they are independent from each other. So what do we say now? We say they're at 10% level of significance. There is enough evidence to conclude, because when you reject the null, that means you kind of support the alternative. Conclude that the number of hours volunteer and the type of volunteers are dependent on one another. They are dependent on each other. The question was asking, are they independent? We don't have enough evidence for that. But based on the result, we say that we have enough evidence to say that they are dependent. Now let's see how we can use the online calculator. So if I open the online calculator, calculator number 22, you will see that it says the test for independence. If you click on that, it's asking you to put all the numbers here, but just the observed one. Okay? You don't need to put the expected one because it will be calculated by the online calculator. So based on how many category do we have for each of the variable, we put the numbers here. And if I put the numbers here and 111, so it may take time. Okay? You just put all of the expected frequencies here. Expected frequency can be done faster. Okay, let's see. 111, 96, 48. 111, 96, 48. The second variable, 96, 133, and 61. 96, 133, and 61. And the last one is 91, 150, 91, 150, and last one is 53. You just need to put the observed frequencies, no sum, no expected, and then just calculate. And you see that the test statistic is 12.99, and we got the same answer here as well, 12.99. And if you need the p-value for your question, that's a p-value. But you know, anytime you're using p-value, you are comparing the p-value with alpha. So comparing p-value with alpha tells you if you need to reject or fail to reject. The alpha was 10%, that means 0.10. Is p-value less than alpha? Yes. It means I need to reject the null. And if I reject the null, that means I'm rejecting that they are independent. So it means that they are dependent and they are related to each other.